Hi. In the last session, we talked about multiplexers in VHDL. We've seen how to write a VHDL design for a combinational multiplexer and registered multiplexer. Now let's talk about shift registers in VHDL, and we will explore how to implement a shift register in VHDL. A shift register made up of flip-flops, and they are connected in series. Like output of one flip-flops goes to the input of next flip-flop. So this structure is like a chain of flip-flops. Shift registers are versatile and they can be used for converting serial data to the parallel data or parallel data into the serial data, depending how they are being used. They are also used to create variable and synchronized delay in a digital circuits as well. So flip-flops are the main component for shift registers. Hence, to design them in VHDL, we need to use registered process block. So this example is 4-stage shift register. Now, before writing the code for this design, let's understand it first. This shift register has a chain length of 4, means you will need 4 flip-flops to design this shift register. Means chain length simply tell that the number of flip-flops in your shift register. Now let's look at the input signals. This is D in and it goes into the input of first flip-flop. Next, all the flip-flops are connected in series and output of one flip-flop goes to the input of next flip-flop. So output of first flip-flop connected with the input to the second flip-flop. Then output of second flip-flop connected with the input of third flip-flop. Same output of third flip-flop goes into the input of fourth flip-flop. Now, this shift register has chain length of 4. So the output of fourth flip-flop is the final output. Means you are giving all your bits or data sequentially to this shift register. And if you want to see all of this input data at the output, means if you want to get parallel data from this serial data, then you can connect your 4-bit output to each flip-flop. Like you can see in this diagram here. Means this module is kind of a serial in parallel out system. So this is one use case of your shift register. Now you will see that all these flip-flops are sharing the same clock signal and reset signal as well. We have also added one more input, that is shift enable. And when this is enabled, your flip-flops will pass out the data to the next flip-flop. And if it is disabled, then these flip-flops will do nothing. And the last signal is output D out, which is 4-bit signal. Like we talked about that how we can get parallel data on this signal. Okay, so let's write the code for this shift register in the next slide. Now we have already covered generic session, right? So we know that how to design a flexible module. And this is the practical here, that how you can use generics in your VSGL designs. So quick brief that we are writing a code for that shift register and we can also adjust the width of it. So we will use generics and attributes in our code. In this slide, we are declaring library and entity of our module. So library and package declaration includes library IEEE use IEEE dot std underscore logic underscore 1164 dot all semicolon. Next is entity declaration. So this is the entity declaration for our module. Entity shift registers is generic bits colon integer bracket closed semicolon, then port clock colon in std logic, reset colon in std logic, shift enable in std logic, d in colon in std logic, d out colon out, and this is std logic vector, bits -1 down to 0, bracket closed semicolon, and entity semicolon. So our module name is shift register. Then we defined a generic named as bits and it is an integer data type. So now you can adjust the size of your shift register. Next, we define the ports of our module. So from the block diagram, we have one clock input, one reset input, one shift enable input, and one data input D in. All of these ports are STD logic type. Then we have data output port D out, and this is STD logic vector signal. Now the important thing is that the range of output signal is not fixed here. Instead, we have used generic parameter to define this range. So if you put 4 in generic, your range will become 3 down to 0. And if you set 8 in generic, then your range will become 7 down to 0. So this is completely flexible now. And at the last, we terminated the entity declaration. Now next is architecture part. So this is the architecture code. Don't afraid with this. We will explain it line by line. So let me read it first. Architecture. My design of shift registers is signal D6 colon STD logic vector D out range semicolon. Begin shift register process colon process reset comma clock begin if reset equals to 1 then D6 gets the value of others are 0 semicolon. Else if at rising edge of clock then if shift enable equals to 1 then D6 gets the value of D in concatenation D6 D out left down to 1 semicolon and if then D out gets the value of D6 semicolon and process and architecture. So we started from architecture declaration line. Then we define signal D6 which is same as D out means same data type and same length. Although this is not needed to define for this example because we can straight assign the data to the D out. But this is just to explain you that how to use signals in your VHDL designs. Then we start our architecture from begin keyword. Now this is synchronous process or you can say registered process. So we include clock signal and a reset signal in the sensitivity list. Next, we begin the process block with the begin keyword. Then we write the reset condition first. So when reset is applied, all the outputs or all the flip-flops output are set to 0. Now we have covered this in the last session that how to assign values to an undetermined length vector like here. So we used others keyword here. If you are not clear about this, please watch my previous session on others keyword. So this statement will set 0 to all the output bits of vector signal. Next, we checked for the rising edge of clock signal. Now, there are many methods that how you write your code in VHDL. For example, for this design, you can instantiate flip-flops as component, or you can use loop for instantiation each component individually. But I have used this one-liner, and it will also do the same job. It might look confusing at the moment, but don't worry, I will be explaining this in next slide. But before this, let's terminate our if statement. Now, before terminating process, let's move our internal signal data to our module output. So we moved D6 data to the D output. Then terminate the process statement and then terminate the architecture body. Now, let me explain the main statement. And this statement is D6 gets the value of D in concatenation D6 D out left down to 1 semicolon. So we have D out definition as well, like D out colon out std logic vector bits minus 1 down to 0. Suppose bits value is 4. So the D out range will be 3 down to 0, right? Because bit value is 4 means bits minus 1 is 3. So it become 3 down to 0. Now coming to the second statement. This is D6 gets the value of D in concatenation with D6 D out left down to 1. So what is D out left? It is 3, right? So we already covered this in the attribute section. So if you have any doubt, then please revisit the attribute section for that. Now coming back, so we can write these lines as D out colon out std logic vector 3 down to 0. D6 gets the value of D in concatenation with D6 3 down to 1 semicolon. Now let's focus on this assignment. On the left side, we have signal D6. It is 4-bit long, right? Now we are assigning D in concatenated with D6 3 down to 1. So length is still 4. 1 bit is coming from the input D in and remaining 3 bits coming from the trimmed D6 signal. How? Because D6 is 3 down to 1 means D6 3, D6 2 and D6 1. Now look at this table. We start from the leftmost index. So index 3 is D out 3. Index 2 is D out 2. Index 1 is D out 1. And index 0 is D out 0. And when there is first rising edge of clock signal, we inserted D in at the third index and shifted all the indexes by 1. Means D out 3 gets D in, D out 2 gets D out 3, D out 1 gets D out 2, and D out 0 gets D out 1. So think a bit that can we map this with these 4 statements? Here is the breakdown of the elements on the right hand side. The leftmost index, which is index 3, has input D in. At index 2, we have element at D out 3. At index 1, we have the element of D out 2. Finally, at index 0, we have the element of D out 1. So we understand that we can write each element like this. And this is the visual presentation of it. We start the assignment from left. So first, D out 3 will get D in. Then D out 2 will get D out 3. Then D out 1 will get D out 2. And finally, D out 0 will get D out 1. Now just give a quick look at this block diagram and signal mapping. It is same like we have explained in the last slide. But now we are at first rising edge of clock signal. And this is the hardware representation of our assignment. And because these assignments are within a register process block, so it generated a flip-flops for each D out element. Therefore, there is a flip-flop for D out 3, then for D out 2, then for D out 1, and finally for D out 0. And at every rising edge of clock, data is shifting to the right. This is the detailed explanation that what is happening at every rising edge of clock signal. Although you can easily understand it if you are clear with the last few slides. But still, let me quickly explain it. So at first rising edge of clock signal, we start from the first assignment. We moved D in to D out 3. So this is implemented by first flip-flop, labeled as FF1. That was the leftmost flip-flop in the picture, which D in was connected to the input of this flip-flop. And you can see now D out 0 is moved out from this range. Means D in is inserted in place of D out 3 and all the other bits are shifted to the right. Now at the second rising edge of clock signal, so D in shifted once again and now it is at D out 2 position. And rest of the bits are shifted once again to the right. Means D in is moving through the second flip-flop now, which is labeled at FF2. Now at the third rising edge of clock signal, D in shifted once again and now it is at D out 1 position and rest of the bits are shifted once again to the right. Means D in is moving through the third flip-flops now, which was labeled as FF3. Now finally at fourth rising edge of clock signal, D in shifted once again and Now it is at D out 0 position, and rest of the bits are shifted once again to the right. Means D in is moving through to the fourth flip flop now, which was labeled as FF4. So this is how our single line of code worked as shift register. And because you have used generics in your design, so you can use this with the length of any signal. Well, we missed to explain shift enable function. So here is a quick brief. So we said shift operation will only work if this shift enable signal is asserted. So we need to do something about this. So we placed our shift operation inside one additional if condition. So now our shift functioning will only execute when shift enable is equals to 1, and that's it. So this is our final VHDL code for parameterized shift register module. You can use this module to implement a shift registers of any length just by setting the bits parameter. We have also seen serial to parallel conversion using this shift register. And if you get a single bit output like dout 0, then it is something like synchronized delay. Because whatever you give as an input, that will only get at the output after 4 clock cycles, or whatever the number you set in your generic value. So it added delay for the n number of clock cycles. Okay, so that's it for today. In the next session, we will be talking about serial edges and we will design it in VHDL. So stay tuned for the updates. If you did not subscribe till now, then please do subscribe to learn and grow community for regular updates. If this video is informative, then please like this video, comment on video, and don't forget to share. Thank you for watching.